talking about the practical techniques for improving analytics capabilities.
Kuwabara.
Thank you for your introduction. I am Kuwabara. And in order to improve the analytical skill, I'd like to present. And I am from FFRI Security. My name is Kuwabara. And I am doing the plugin for Kuwabara X64. And also, we are developing the plugins for analyzing Go language binaries, and I'd like to present my insight gained. And I'd like to talk about the outline and the Go language analysis issues, as well as for the people who haven't experienced much about the analysis of malware. I'd like to talk about the basics, and if you have already done the analysis, I'd like to talk about the advanced areas, and I'd like to talk about the current status as well as issues. The benefits of using Go language for malware development is easy to develop Go language, and the cross-compile is easy. And this allows less effort for developers and be able to create malware easily for different platforms. And the actual reference is Electric and Chaos malware, and not just for Windows, but the Linux and Mac OS malwares confirmed. And also in Chaos, ARMware Intel architecture, as well as PowerPC and mixed and other wide area architecture binaries confirmed. And in case of Chaos, it was discovered in 2022, and there are other Go language malwares discovered last year. So we expect the tendency of increasing malware for Go language. And the Go language was presented on the first day. And so I believe you have some understanding about the Go language, and the Go language malware increasing, and we need more analysis. And the Go language malwares are hard to analyze. We need to solve that issue. And the problems are, first, there are so many volume, and not just a simple hello world 10 lines, but have more than 1,000 the variables in it. With electroword, there are more than 8,000 definitions. So it's such a big volume. And also in analyzing each functions, if you are going to identify functions, you need to find system calls. And calling Windows API through register is involved with call command. Therefore, it is hard to analyze. With Go language, the default get block address and obfuscated structure. Go language have some specific data as well as the rule for invoking, and the data flow is hard to analyze. In order to deal with these issues, there are some open tools. For instance, solving the names of functions as well as the string, and even if the functions are in large volume, be able to narrow down the scope of analysis, which makes it easier to analyze. However, the tool has some problems. The tool cannot be reused for a long time. And the Go language malware, this is a feature of Go language. If the Go language upgrades its version, the existing analysis tool reference data is changed. Therefore, the emerging malware, if it's an upgraded version, the tool cannot be applied anymore. The second problem is obfuscation. And this happens with the general malware, but there is a tool for Go language, and the names of the functions will no longer be a hint for analysis, and therefore the string will not make sense anymore. Not just existing tool. If you use existing tool as is, it will be hard to analyze. So need to deal with the upgraded version of Go language as well as obfuscation. And in the basic analysis, Go language malware issues, which is hard to analyze, can be solved with the tool. And if the tool can no longer be used, such as obfuscation as well as upgrade of Go language, I'd like to explain. And first, I'd like to talk about the basic analysis. Before talking about the analysis, I'd like to talk about some of the codes which is unique to Go malware briefly. The string and interface. The Go string, unlike ordinary C, binary is not in terminal, but the structure defined, and there are two fields. Strings are represented as structs of null terminated and unique types such as interface. And there are multiple types, but there are pointers, and those are the data pointer. And the data form the information pointer is going to be explained later. The data structure size and whether it's structs or pointer, that information is held. And we're able to get that sort of information at the analysis. Next, about the slices. The slices can be dynamically changed. This is almost like an array, and the pointer for array as well as length, and also the memory held. And not just the slicing, but also the variable arguments. For variable part, there are two strings given as the argument, and then assembler with a length to be able to represent as such. Next, about map. As is presented, the map access and assign functions and argument, the map mode, map type as well as object and key, and the return pointer, and to get the value and to set. And also the type of map is taken, and this is same as interface that we saw earlier. Looking at the type of you'll be able to know the value, or the string or int is in the value. You'll be able to get that sort of information. Finally, about the invoking rule, the Intel 64 gig, and with the existing C, the argument is RCX, RDX used, and the RLX may be used for model value alone. But in case of Go language and over a particular version, the arguments and return values are both RX, and so this is completely different from ordinary registry. And if it's below a particular version, only the stack is used. For other architecture, shown below from URL, you can get the source code. It is simple to understand, so please make a reference to this. And for the invoking rule, for the calling rule, how challenging it is, and by getting the data, be able to analyze easier, and you can solve this issue with a tool. And the tool that we are going to use for the presentation is shown in the link below for solving the names of the functions or the argument or the return value, and also the data type extraction information shown. And the Ghidra assembler and recompile, applying this and get the result. And that was a particular feature of Go language. And when I analyze Go language analysis, there are some analysis flow that I'd like to introduce partially. In the beginning, depending on the tool, the function names are taken. Therefore, the main function is identified. So we'll be able to see what sort of functions called from the main. And then after that, the names of functions as well as file names as well as the information of structures can be taken by the tool, and they'd have to confirm that. So if you confirm these information, you'll be able to know the names of the function that might be attacking, and we'll be able to do the exception.
And then the functions that you assumed at the next stage, whether that is correct or not, will be confirmed. And so under such flow, the malware functions can be understood, and we get into the detailed analysis in accordance to each of the applications. And so we use the electro-rat in this case. And the analysis flow is similar to the previous one, but I've skipped some of it. This is the main portion. On the right, we have the main functions and compile results, and you can call the functions the net HTTP client gets, and that's the standard library function. So search information, and bottom right, main set auto start, main get auto start, and this is called at the rear, and so these functions can be confirmed, like with a C2 communication. We can assume that these are behaving accordingly. Next, we have the function name and the file name. On the right, I showed you before, we can call this out from the tool as introduced earlier. If you confirm this, WebSocket, upload file. And these are the functions names. And you can assume that the file is taken outside. Next, go auto start from this string. You do auto start. That is another assumption that you can make. So based on this, we confirm the contents. And in the bold letters, I will go over these two areas in bold font. So information gathering. And so what's the configuration? Under which the calling is taking place. To confirm that, we have a call tree and WebSocket and upload. The WebSocket, the main function socket connect, that's where it's called from. Next, upload file. From main socket connect 1, function 1. And this func 1, the calling source is quite ambiguous. And this func 1 function is a Go specific thread. And it is called via this. And with existing thread, it's the same. When you create the thread, you have the function pointer to make the thread, and you execute as a thread, and such is the configuration. And so the calling method is similar, not called tree, but you refer to the functions instead. Now, information and theft. On the right is upload file content, and at the top, we have towards the map, the value allocation for the map. And you look at the key, there's a file string, and the allocated value it is upload file argument, and so we don't know the argument type, and so we look at the map type, and the first argument, and it's a string, and you see that, and then you get the key and the value. We know that both are strings, and so what is allocated here is probably a upload file path, according to assumption. And so the map created here, in the subsequent process, we do a request, an object, and it's given to set file. And after that, we get the rext, and execute. And there is a post string. And so we think that the file is taken outside through post to steal the information. And it's almost sure. Next, auto startup settings. And you can see I will skip the calling source, but the path is a go start. And you can see from the string, it says GitHub. And so it's OSS library is being used with a decompile result. It's not shown here, but the readB of this repository, you look at the figure, and the attackers are doing the auto startup settings. And inside OSS, there's a shortcut file, and it's in startup folder. And we can see it in quantity. And other than that, with Electrorat, OSS is being used, and it's all from Windows on Linux and Mac OS compatible. So attackers can use these multiple tools. But the repository path can be taken, and we can make an efficient analysis that way. And so frequently used OSS libraries. And in the first day, the similar information was given, so I will skip this. Next, through these analysis, we're able to see the function of the Electrorat, and so we'll get into the detailed analysis. And this time, the malware, the main C2 communication, is where we focus. This is the main function, and it's a Windows socket connect, and it is called from that function. So let's look at that. And so looking at this function, the content is sparse. There's establishing the communication and the calling main socket connect func1. And there's a main object, and the object for communication is created, and it is in func1 argument. And this func1 content with and internally, we have the typical C2 communication, and we see implementation of this of the feature. And we look at the file and take out the file, and that is one of the function here. And this is a receive instruction and pass command. So first, assembler, the top part of assembler, and this is a common object for the argument, and we receive the instruction, and the data received through a number of object go to a decoder object, and it is converted to the structure, and it is passed on. And the converted object, window.command, that is the structure, and the field information of the structure. And on the left, you can take it out with a tool. And so the analysis is very easy to look at. And in the first field, we have type. It's under the assembler. It is compared with the string, and that is the actual instruction. And there's a rank 1. That's what's compared against. And so we look at the rank 1 and see how the results are being transmitted. This is showing it. So with the run command, you execute the command, and the command that is executed is coming from C2 as a main command. Main command dot data under field, and internally there's another structure, and it's a command field. It includes a string, and this information is the function. Is given to the function that is that will execute the command, and as a result of the command being implemented, that comes as a return value and is converted, and it is sent to the C2 server, and that is the flow. So we did a detailed analysis, and we looked at it from the Electrorat, and after the analysis of the sample, we may see the other infection, and it may be implemented in another platform, and it may belong to the same family. And so we have to make the analysis efficiently as an analyst. But this time, we are going to look at how we should deal with this.
In case of Go language, binary assembler line numbers can be extracted, so you'll be able to compare in detail. And I'd like to compare the names of the file. On the right, this is the sample that we compared. On the left, this is a new sample. And this shows the Chrome Windows.go file, and Windows.go file is deleted, and the new download file is added, and the change of file in case of Electrorat command, how does it affect the command, is shown in this table. And this is the number of the source code line, and the command structure shows the structure is same. And there was the increase and decrease of the file, and the yellow is a Windows file added. It was removed, but here the keylogger command is left, so only a refactor. And the next is a download file added. And together with this, add file command is also added. This is from C2. File is dropped. And the Chrome window file is removed. And together, the Chrome password extraction command is deleted. This function within Electrola, the key is retained, and to deploy and execute, that is a flow. With the add file command, the execution file is received from the C file, and then maybe it was removed. This way, between the samples, you'll be able to compare the difference. If there is any change, you'll be able to focus the analysis, which reduces the time spent on analysis. Next, I'd like to talk about the advanced analysis. The Go language malware is analyzed, and then you'll be familiar with analysis, and maybe you have some favorite tools such as Hydra and IDEs. And you'll be able to find your own favorite tool. And these tools, if you want to analyze a new malware, maybe you will no longer be able to use some of the tools. And as introduced, because of the upgrade of the version of the Go language, this problem is caused. And with the upgrade of the Go language, the file structure changed, and therefore the tool can no longer be used. And this time, when we face that problem, you want to continue using your favorite tool, and the metadata information that the tool makes a reference to, and also about the case of fixing the tool is something that I'd like to discuss next. The function names as well as data form information. In case of function information, the stack trace at the panel, the information shown on the is shown, and with the data information, the interface and map reference data is retained. And within the binary, how is it managed? The module data and PC header data is used as structure, and I'd like to talk about more details. First, module data. The PC header pointer as well as data information link retained, and the base address and also the offset, the type link can be used. And the module data structure is huge, and over the past there have been some changes, and the addition of the field have been done a few times already, and the type for the links in the bottom of the module type, and if the offset changes from the front, and the data information cannot be extracted with tool. That happens quite often. The data, even if you don't know the data structure much, will be able to take actions by just looking at the source code. And so please memorize this. This will be helpful later. And the major changes, the data information, the information to make a reference to data, that it's not an offset, but was a pointer, but the types field is added. So the type link became offset. That was a change that took place in the past. Now I'd like to talk about PC header. In front of the PC header, there's fixed value, and other information is a number of functions, as well as to solve the function information. There's a PC offset information, and there have been some changes in the past, and number change or major change, such as PC offset, did not exist, but the ink for the function information, the array was in the end of the PC, and the array can be referenced with the PC offset. So this is a major information or a major change, so you need to be careful. And this way, the information to manage metadata was presented next. Within the binary, where is it located? There are two ways of finding a section or check And using JIT section, there's a PC header. By looking for this section, be able to find the PC header. The other one is use magic. In the PC header, there is a fixed value. By looking for this fixed value, be able to get the PC header value. And the module data retains the PC header pointer, so be able to search the address to get the address. This way you can locate the place and be able to know the management information and be able to get the data next. From the PC header, the function information is extracted. There's a functor we are under bar func structure, and this is same as the previous flow. So I'm going to omit some of the areas. First, it has an offset to the function information and can get the function information. It's under func, and there's some changes under bar func, the offset to the function names as well as the argument byte and also other assembler related information. And the assembler related information is hard to explain, so I'd like to omit. And our blog, I hope that we'll be able to introduce this, so please look forward to it. There are some changes here as well. And with the Ghidra information, how you can get information, this is rather busy slide, and I'm sorry, but we have some. And the PC header on the left-hand side, from the field, the func table, func off field, underbar type gained. Underbar type, entry off and name off, traced to get the center address of functions or the names of functions. This is how we can solve the information. Next, the data type information. Underbar type is a structure to express data type, and underbar type, as mentioned, is an interface or map operation used type information. And looking at this information, for the basic analysis, the information of the size of the data type retained, and data type information, the structure pointers, and depending on the value, it changes. But data specific information is in the end of the underbar type. So these additional information, such as start field information, retained. And there are some changes in the past. If you look at it with Ghidra module data type link, underbar type address obtained, and this time the pointer data type is shown, the 64-bit, so the size is 8. The kind shows, if you get the kind, this is quite unique, 0x1f, filtered. By doing this, you can get the value that I introduced earlier. The pointer specific data, the data type that the pointer points to is retained, and this is underbar type end. And that completes a metadata explanation of Go. Now I'd like to talk about how to fix it, the chaos sample. And the tool is a tool script and to solve the function name. And if you apply with Go 1.15 without applying the binary, the Windows main and within assembler, the names of the functions of within assembler, so I can make sure that it's running properly. There are some that did not run, so there are 2 fixes. And next, the result of applying to chaos. There are a lot of alerts. Within alerts, 0x247 is shown. And this should be the address of the function, but this is not an address. And even if I list up some of the functions, they're of a garbage function name. So it is failing for sure. And with Go 1.15, it was successful, and the chaos failed after that with Go 1.18. So I'd like to talk about the change.
So the magic is being changed. And the function information, and there's an ink information for string for the array, and it is on PC offset, and that is referred there. And there's other changes. On the bar func, you get the function information, and this is the flow, and the pointer is offset, and the base address is changed. Based on that, we look at the source code, and there is some areas to be changed, like the functable array. The address get and base address is changed. We do modification, and we apply to chaos. Look at the top. This is main.main, the function name, and assembler, the called function name is resolved. So by modifying to chaos, it is applicable. And these are the modified script. And it is public at repository at the end. There's a link. So please refer. So version up Go language was explained. So now obfuscation. Chachi is a target sample. It's a Go Fasket. And I'll introduce this. This Go Fasket is Go Fasket. What does that mean? And talk about the obfuscation with Go Fasket. So this is Go Fasket obfuscation. There are two images introduced, and we have the obfuscation of strings and the function name, and it is provided by Go Obfuscate amongst other functions. And as obfuscation, you change the source code name, and so the tools will take out the information, but the names will be obfuscated, and the string obfuscation resolution will be introduced. And so the obfuscate string obfuscation, there's a Golang string, and when you obfuscate, this is output. And by rewriting Golang, you get this. In the second and third row, you get the byte array, and it is returned after it is converted to string. By using this, the obfuscation of the Go string is done. And this function portion, Chachi malware, if you see, then it becomes like an assembler on the right. At the top, byte string extraction. After that, and XOR sequence of bytes resolution, and then runtime dot string byte to string function. From byte, it converts to string. So the byte string taken at the top, we have non-persist, and we think it's a flag for persistence that is created. So anonymous function in assembler, how does it appear in a Go language? And there's a .func string, and the Windows socket.1 will probably be corresponding to this anonymous function. And so based on that information, this is resolving obfuscation. And so what are the functions? And these are anonymous function. And so we identify that. And a byte is converted to string. And so runtime byte to string alone is called. And we drill it down to those functions. And after drilling down, we have to take out the string. We got the row information. So the source code, second, third row information is taken with the tool, and then we get the byte string extraction. So that is easy to do, and it is converted with XOR, and you can rename a function, or you can add comment, make it easy for the users to see. So with this implementation, we created a script, and malware Chachi was used here. So Chachi malware, this is main.unit, and you initialize, and you look at the function name at the top is Java GBC, and at the bottom, or Oracle JDB driver, that's a string. And to see that the obfuscation was resolved, and the analysis became efficient. Having said that, just by removing obfuscation does not make the analysis easy. So we have to estimate the function and look at the OSS libraries. We find out what is used. That makes the analysis more efficient. So with Go Fuscate, after Chachi, the function name is shown at the bottom, is obfuscated. But if you look at the file information, it is not obfuscated. And we have service.go and service underbar go Windows ago. And so there's a function to use the service according to assumption. So a service.go or file name, and prior to that, there is the long string which is obfuscated, but it is has slashes in between, so we think it's a GitHub path, maybe here. But because it's obfuscated, we don't know what is used. We need to investigate. And the obfuscated string at the end, we have server window.go, and what I showed you before, the file name, the corresponding function name. With the extraction of the string, we can get these other strings. And so this information will be retrieved and searched in Google. And we hit a number of repositories and confirming this. At the top, we've got the file name matching and also the row numbers too. We think this is correct. And these are the repositories that's being used. This OSS service, Cardinals, is matched. But the row number, with a string obfuscation, number of characters appeared in a number of rows, and it was converted to anonymous string. Then you get the deviation of these strings towards the back. And so we identified OSS libraries. We identified others too. So let me share this with you since it may be useful to you. So the summary. So we did a Go language malware analysis, and the binary is not easy to analyze. But I also shared with you information about the tools, how to cope with this. The difficult analysis can be made easy with tools and using the function flow, or maybe a good reference. And after that, when you can no longer use tools, then we have to correspond to the Go language version. And I also showed you some other measures. And when you tackle with a Go language malware, if your analysis become more efficient, then that would be something that make me happy. And so there's lack of tools still, like compile to, like when the register is used in argument, the same register is used for the arguments in the string, and the precision is not so high yet. And also the dynamic tool, like the debugger tools and tools that analyze the information, is quite rare to find. Lastly, these are the tools we introduced, and this created the script, and it's shown in this link. So please refer to this. I thank you very much for your kind attention.